So the theme of this BISH Bash is voice cloning using GANs. Just kind of an agenda. Welcome. Hey, welcome. I'll do a quick demo in a second, but I'm going to actually first turn it over to Zafar, who's going to explain what BISH Bash actually is. We'll open the floor for some quick announcements. And by that, I mean like 10-second elevator pitches. If your company is hiring particularly, that's a great example of something that we should shout out. Or if there's something that you think this community needs to know about, you'll unmute your. What I want you to do, actually, think about if you have an announcement you want to say. There should be a raise hands button. It's usually under reactions. If it's not under reactions, it might be under participants. We're smart people, we'll figure it out. So the way I make my Stanford students do this, press raise hands, and then I'll work through the line and just call your name, and then you can give your quick announcement. I'll give a quick demo, and then we'll actually learn about voice cloning using GANs and spend most of our time there. We're going to use the raise hands feature. I'd recommend using that. If you have questions, do that, and then that'll let the speaker kind of take a break at some point and work through some of their questions, or you could also text it in as well on the chat functionality. The last half hour, since we've already started kind of realizing how much we all have in common, we're going to try doing some breakout rooms. Zoom has a cool functionality where with one button press, I can send us off into randomly distributed groups, of small groups, kind of like we're all sitting at tables together just talking. We'll try that for like 10 or 15 minutes. I'll swap up the groups once, try it. We'll just see what happens. And if you do need to leave, well, that's okay. Hope everybody's enjoying the cocktails that we've provided and the food and the pizza. It's wonderful. So thank you to Descript for hosting. It's very low maintenance. Zafar, I'd love if you could explain a little bit about what is BISH Bash, and you can just tell me next slide and I'll advance your slides for you.
All right, sounds good. Well, first of all, thank you a lot for hosting, even if it's virtually hosting the events. This is the first virtual BISH Bash that we are having. And yeah, Jay was kind enough to show us how we do it so that next time we can have, because this is going to last for a while. And I think following this pandemic, we're probably going to have more virtual events happening. So it's nice to learn how to do this. So yeah, let's move to the next one. So what is BISH Bash? So BISH Bash is an informal networking meetup for, originally was meant for people just in the Bay Area interested in audio signals, but this kind of extended to more than just audio signals. You know, we see that this is bleeding to other fields as well. And even if you work on audio, I'm sure you're interested in other things like, I don't know, video, images too. And also why I said it's more than San Francisco is that this is extending to people outside of San Francisco, not just because this is virtual, but because also there's going to be other BISH Bash happening around the world. I'll show you later in the next slides. The other thing I wanted to say, typically this was hosted by, it's an informal meetup hosted by like companies involved in the field of, you know, audio signal processing. And we can see here a list of, you know, all the hosts that we had in the past. And I guess Descript is going to be one of them now. So what happens is that typically when it was not virtual, the host is kind enough to provide some food and drinks. And we get to in a room, some presentations. So there can be some show off, like the host can do a bit of demo, show what they're doing, like Jay is going to do. And the community, the research community, get to know more about the company, and they get to know more about what's going on, share thoughts, talk to each other, etc. Yeah, let's move to the next slide, please. So yeah, as I said, it's mostly like an informal networking meetup. So the presentation are almost like optional, I would say. Originally, this was meant for people to meet. So you meet with other people who have similar interests. You learn about the latest and the greatest in the field, but you make friends, you make connections. So this could be like, I don't know, meeting your next boss or meeting your next employees or meeting a friend you're going to work on the same project, things like that. Next, please. And yeah, keep the momentum going. This is important. Like if you if you know other people or the company who would like to, or the institution would like to host this meetup, because it's not just companies. We had Karma at Stanford that hosted this meetup. Please let me know. So I put some link on the slide, but I will share them too in the chat. Yeah, we have a LinkedIn page and a Twitter account too, I guess. And next one, please. And as I was saying, this originally we did the BISH Bash in the San Francisco Bay, but we tried to like kind of extend this idea everywhere on the world, since this is working so well. As I said, today is the first virtual San Francisco-based BISH Bash, but we have also a Tokyo BISH Bash that happened recently that was supposed to be hosted physically, but became like a virtual one hosted by Line, for people who know that. I will share also the link. And we had also a Paris BISH Bash that happened also recently, which was actually physically hosted by Deezer. And I'm talking to some of the friends who maybe will see the next New York BISH Bash or London BISH Bash or anywhere BISH Bash. And if you're also interested in, trying to make your own BISH Bash, where in Montreal, for example, it's not a lot of work from the organizers. You just need to basically send emails left and right, find hosts. So yeah, it's a cool thing to do. I will share those links on the chat. And yeah, thank you again to Jay and Descript for hosting this. Oh, there's another one. It's on the slide. I forgot. Can you move to the next slide?
That's all I got.
That's all you got. Okay, well, never mind. So yeah, we were supposed to have one hosted at University of San Francisco, but that got postponed because of the pandemic. We will try to maybe have the next one hosted virtually, but still at University of San Francisco. So we'll let you know.
Awesome.
Thank you again.
Fantastic. You are so, I really appreciate all the work that you've done and the other organizers have done over the many, many years to kind of grow this community. We've got 58 people currently on here, and I think that's only going to grow in the coming weeks. Let me give you the official welcoming.
Welcome to the Bay Area Signal Hackers Meetup, or BISH Bash. Jay and I are thrilled to talk about the intersection of artificial intelligence, creativity, and voice modeling. I'm a voice double based on a real person. They trained me based on only 10 minutes of my recorded speech. Anyone can create their own voice double with Descript. Please make sure to have your model say hi to me. It's lonely sheltering in place in the cloud. Thanks, Jay. I appreciate it. Back to you.
Well, hopefully you heard that, or I've just been staring at my screen for the past 30 seconds. That is Overdub, and that's what the focus of tonight's talk is going to be. I spend almost all my time showing people the product and working with users and companies on the productization of this technology. Tonight, we're actually going to go behind the scenes and talk about how it was actually made. So as this voice double is saying, that is a voice double of some voice talent that I work with. She owns the rights to her voice. She assigned it to me so I can use it for some customer demos because her voice is more pleasant to listen to than mine. And just by typing in the blue text, it sends something up to the cloud, and I could just say, have a nice day. Good to see you all. And just by typing that in, it's going to generate the overdub. So basically the text is being sent to the cloud along with the voice style information, along with the audio that surrounds it. And then now we have.
Thanks, Jay. I appreciate it. Back to you. Have a nice day. Good to see you all.
So that is, very text to speech. One of the reasons that Descript acquired Lyrebird about 6 or 7 months ago is to make this technology available to podcasters and to make it available to anybody who's basically doing narrative content. And here's a couple of examples of using a voice double in action. So here's Gregory. What you're going to see here, this first line is Gregory just talking normally, and the second line is where we've replaced what he said in yellow with what we typed in purple. So it's kind of a before and after of mixing his natural voice with his voice, double voice.
He'd left this sheltered, conservative childhood and entered a world where people were pessimistic about the Vietnam War. He'd left this sheltered, conservative childhood and entered a world where people were concerned about climate change issues. He's one of the only people who knows what Reagan is about to do. He's one of the only people who can anticipate what Trump is planning to do.
So that's one example. I'll give you an example with a different voice.
You have energy, content, charisma, arc. There's all these different things. You have energy, content, enthusiasm, arc. There's all these different things.
He'd left.
So these are examples where someone will say something as part of their interview, as part of a call to action, long form production. We make mistakes, we say things, and you have to come back into the studio and re-record that. And more than likely, you have to come back in the studio, re-record that, and then your re-recording or your overdubbing doesn't sound anything like it does the first time. So using your voice double, you can just type in the text or phrase that you said incorrectly or new material, late breaking information, and it gets generated. The platform you're looking at right now is Descript. So I'll make this a little bigger so you can actually see it full screen. And Descript is like it looks. It is a platform for editing audio and video that is as simple as editing text. Let's say we have the Gettysburg Address, but our voice actor, Gabe, didn't do such a good job. You can think of this as kind of like a Google Docs for audio. So what we did, we either drag in an audio file directly into here, or we can actually record it directly into Descript. The transcript is generated in real time, and then once it's generated, it is automatically synced to the audio. So now we can, by the way, we can share the files and send them and collaborate in real time. In this case, let's see what we have here.
That we should do this, but in a larger sense, we cannot dedicate, we cannot consecrate, we cannot hallow this ground. The brave men.
So, okay, I can very easily just visually see, much easier than just looking at a waveform with no context, that it starts with, in a larger sense, the first one was bad. And then we cannot dedicate, we cannot concentrate, we cannot, there's two cannots. I don't know why. Let's just go back.
That we should do this, but
I'm going to pause right there. There's a really long pause between the end of the sentence and the word but, and then another really long pause. If you look down here, you can see the word bar. So we take the alignment of the words that we recognize and put it on the waveform. So people like me who are lazy can just click on the word but and drag it to the left. And here, I'll zoom in, click on the word in, shorten the spacing. Editors do a lot of this type of work to get the pacing of your podcast sounding great. So now let's listen to this.
altogether fitting and proper that we should do this, but in a larger sense, we cannot dedicate, we cannot consecrate, we cannot hallow this ground.
Awesome. So in the same way that I've been kind of copying and text or copying, pasting, doing things like that, yes, I could delete this and put it up here. And now I'm moving entire paragraphs around where maybe they make a little bit more sense. Let's show you this in action. So this is a snippet from the Andreessen Horowitz podcast. The way that they do this podcast, they do it with Descript. And behind the scenes, it's a 5 microphone setup. So each speaker has their own mic. It looks nice and clean. I think they have noise gates on the side that only open up when somebody's talking. But we've got these nice, clean 5 microphones that are aligned into one transcript. So that's all you have to worry about when you're editing, not the fact that there's 5 channels in the background. And let's listen to one speaker, somebody named Dave.
Great. Accuracy, the ubiquity of microphones.
Yep.
Any other
factors?
What I'd add is the cost of compute has come down enough that you can run very expensive deep neural nets to do a lot of processing that even 5 years ago would have been expensive, and now we're talking about putting these things directly on a phone.
Sounds okay, and that's a very off-the-cuff answer. There's a lot we could do, though, to actually make Dave sound like somebody you would hear on the news or on the radio. First thing, you'll notice we've underlined this. So once we actually can understand the text that people are saying, we can actually do smart things like ignoring the or recognizing that it is a filler word, a class of words that we just use to fill in space when we just should be thinking of something else to say. In this case, I'm going to say ignore all, and that's going to tell Descript to either delete them or not even play them. And he has the word these here, which actually makes no sense to me whatsoever. So I'm going to delete that. And he has, I think this is a...
And, now we're talking about putting the...
Cool, that doesn't make sense. I'm just going to hit delete there. All right, let's just see how this sounds, just with a few changes.
What I'd add is the cost of compute has come down enough that you can run very expensive deep neural nets to do a lot of processing that even 5 years ago would have been expensive, and now we're talking about putting these things directly on a phone.
Cool, so I can make edits in real time. The last thing I'm going to do is just show you, you heard a couple of people chiming in with a...
And
all right, great. I can just easily jump back if I want to and just do some very basic waveform editing in the sequence view. In my experience, I really don't do that very much. I spend most of my time in the transcript, and ideally that's the goal. We want people to do as little waveform editing as possible and have the AI do the rest. I think that is a good place to turn it over so you guys you have a good motivation on what we're trying to do here, why the technology is useful, and I don't know, you probably want to know how it actually works. And with that, I get out of my comfort zone. I turn it over to people that do know how it works. So I'm going to turn it over to Rithesh and Kundan, who can introduce themselves and start their screen sharing. They're on the research team at Lyrebird and Descript.
Hello, everyone. Are you able to hear me well?
Sound great?
Yes. I am Kundan. I am research lead at Descript. I am one of the co-founders of Lyrebird, which kind of pioneered this voice cloning technology around 3 years ago. Very excited to be here and talk about what we do at Descript now, like bringing this technology in the hands of users. So basically what we are going to talk about is first, I think Jay has already covered what is Overdub. So I will just briefly talk about what's the technical definition of Overdub basically is. And then second point, whenever we talk about voice cloning, the first question that people ask us is that, oh, how do you ensure that it's being used ethically? And I want to take this point very upfront and going to talk about how we have designed the system in the first place that make sure that we ensure or we enforce the ethical use of Overdub. And we will show how it is baked into our Overdub voice creation flow. After that, I will hand it over to Rithesh, who is going to go deeper into the deep learning aspects of voice cloning, specifically focusing on how we use GANs to do voice cloning. And at the end, we will have some more demos. So let's get started. So it is Rithesh and I who are presenting today, but it's really a work of an incredible team that we have at Descript working on Overdub. So what is Overdub? I think Jay covered it, but I still thought that to just have an example here. I'm not going to play the video because you have seen it live in action. So I'm just going to describe what it is from technical perspective. So essentially, you have this training data of 10 minutes of audio recording from a person, and then you want to create a digital copy of that voice. which we call overdub voice. And once this digital copy is ready, you can use it to enable editing. So you just type text and it produces the audio in that specific voice. Whenever there is some contextual audio around it, it tries to make sure to use those so that the generated audio blends right in there. So, but of course, like we are doing voice cloning. How do we ensure that, you know, like not like I am a user of Descript, so I should just be allowed to create my own voice. We bake this principle inside Descript because, of course, like safety, security, and ethical use of our technology is one of the primary concerns that we have. So to clone a user's voice for overdub, they must submit a recording of their voice, reading a specific script that we ask them. And in this script, we specifically ask people to read a consent statement that they allow us to create their voice, their overdub voice. And hence, by designing a system in such a way, we ensure that any overdub user agrees to their voice creation, and we never create a voice unless we are provided with this specific recording. And technically, it's very simple. Like since Descript really works on this transcript version of the audio, so you take the recording that user has submitted, you compare its transcript to the script that we ask them to read. And if there is a difference there, we just don't train the voice. As simple as that. So how exactly this voice creation flow work? We give user a script to read, which contains this consent statement that, oh, I allow Descript to create a digital version of my voice, and I fully understand that a digital version of my voice is going to exist after this. I will be the sole owner of this voice unless I give someone access to this specific voice. So once they submit the training data, we verify the training data. Specifically, we verify if it is the same recording or if user has read the same thing that we ask them to read. After that, the technical part comes. We pre-process the data. We have a bunch of deep learning models customized for that specific voice. And then at the end, we just serve the specific overdub voice for that user whenever they're using the app. And we have designed the whole access control so that only the voice owner has access to the overdub voice in the first place. So now I will hand over to Rithesh, who is going to introduce himself and then talk about why overdub is hard to build and what we have done to ensure to solve this hard problem. Rithesh, up to you.
Yeah, thank you, Kundan. Can you stop your sharing? Yeah.
Yes.
So go there. So first, hello everyone. My name is Rithesh Kumar. I am one of the AI researchers at Descript, and I'm definitely happy to be presenting today. And since Jay said introduce yourself with a favorite color, I think I'm going to go with blue. I think that's my answer, yeah. So let's get started. So just one thing I want to put it out there. Please feel free to ask your questions, either raising your hand or typing it in the chat, and Jay can interrupt me whenever, just quickly pop in a question so that it's pretty clear to everyone. Yeah. So
I will interrupt you.
Yeah. Let's get started. So why is overdub hard? So the first thing is audio is very high dimensional, and it's very well known in the AI community that generating high dimensional data is very hard. So we say audio is very high dimensional because the sampling rate of audio nowadays is a minimum of 16 kilohertz, which means there's 16,000 data points per second. and generating data at this resolution is pretty hard. And so the second reason why Overdub is hard is text and audio sequences are of very different lengths. So as a thumb rule, it's one character roughly corresponds to almost 1,000 samples in the raw audio. So you can do the math. It's an order of magnitude different. And another reason why they are of different lengths and there's no direct relationship is because the same text can be spoken in multiple ways. So a person can speak very fast, very slow. They can change their style of delivery, many things like that. And my slide is glitching. Yeah. So the third reason why Overdub is hard is because voice cloning in the wild is challenging. This is because people record themselves in very diverse data conditions. And we also need to work with very limited data because people don't want to record themselves for multiple hours. We need to make do with a 10 or 12-minute recording of their voice. And lastly, the most important thing is that for Overdub to be practically useful, this necessitates very high quality speech with no artifacts, and it should also be fast in inference. Because if the audio has any artifacts, it usually throws people off and they wouldn't want to put it in, for example, their podcast. So these are the reasons why building Overdub is hard. So let's move on to how we build it inside Descript. So the first thing that you see over here is we break down the problem. So in the previous slide, we just spoke about why it is difficult to model text-to-speech directly. There's there's 22,000 samples a second and it's hard. So what we do is we choose to break down the problem into two parts. The first part we call Text-to-mel, which takes the characters, the text, and generates a sequence of MEL spectrograms. And then there's a second network called the MEL-to-wave network, which takes these MEL spectrograms as input and it spits out the raw waveform. So the natural question here in your mind is why this specific subdivision? Why do we do this? So the question is, so the answer is, so we spoke about compute being very hard because the time resolution of audio is very high. So with this MEL-to-wave network, what is now allowed is that you don't have to train on the entire sentence. So an average sentence is around 8 sentences long, is around 8 seconds long. So 8 seconds times 22 kilohertz is like almost 160,000 dimensional. So instead of training a massive network which has to operate on a lot of data, this specific subdivision allows us to work on much smaller chunks. For example, for this MEL-to-wave network, we can train on a small chunk of audio as small as just 10,000 samples. So so one major advantage is that we can save on a lot of memory and compute. And another reason is that the text to a frequency domain representation of audio, like learning the mapping from text to the frequency domain representation is much easier than modeling directly from text to the end raw audio sample. Yeah, so in summary, we build this, we split this pipeline into two components. One is Text-to-mel and the other one is MEL-to-wave. Because it's way more convenient for us to build these neural networks around the subdivision. Yeah, so moving on, let's discuss the MEL-to-wave task. So even though it's the second component in the pipeline, let's discuss this first because it's arguably the easier component, and by chronology, it also helps to talk about this first. So what you see in this diagram is just a very simple API of this network. So the input to this network is the MEL spectrogram, and the output is the raw waveform. So why is this task necessary, and why do we need neural networks? So the reason why the task is necessary is because MEL spectrograms are a lossy compression of audio, So for those in this meeting who are not very sure of what MEL spectrograms are, I'm pretty sure everyone knows what a spectrogram is because everyone works in audio. So what MEL spectrogram means is that we take the magnitudes from the spectrogram and we convert it to this MEL frequency scale rather than operating in the linearly spaced frequency scale. And the reason is because researchers have found that humans can judge differences between lower frequencies much better than the higher ones. So what the MEL transformation does is it takes this linearly spaced frequencies and converts it to a different spacing, which is more linearly spaced, but according to the human ear, when you judge it with a human ear. Yeah. So that is MEL spectrogram. And yeah, so coming back, MEL spectrograms are a lossy compression of audio. So the reason why we say it's lossy is because when we compute a spectrogram, we typically drop the phase. And when we do this MEL transformation, we're further compressing the magnitudes into typically something like 80 dimensions. So that's why we require something like a parametric model, like a neural network, to sort of get back the waveform, which sounds good and does not have any artifacts. And the reason why we use neural networks is that the traditional DSP methods don't work very well. So Griffin-Lim is a very, very popular reconstruction algorithm to get waveform back from spectrograms, and that does not sound well. So that's the MEL-to-wave task definition. So moving on, let's talk about the most popular choice for this MEL-to-wave network in the AI community, which is these class of models called autoregressive models. So what these autoregressive models do is they decompose the joint distribution using the chain rule of probability. So you see the equation here where you factorize the joint distribution of the waveform as a product of the conditional probabilities. But at a high level, what this means is you want a model to approximate this conditional distribution, which represents predicting a sample at time step t conditioned on all the time steps in the past from 1 to t-1. So what it's going to do is it's going to generate a waveform one sample at a time, where each sample is conditioned on all the past samples. And that is what you get, and that is what you get a sense of with this animation as well, where you see each sample being generated one at a time. So autoregressive models for audio generation. So autoregressive models have been very, very successful in the AI community. So autoregressive models has worked extremely well on many domains. It has succeeded for audio. So it majorly succeeded for audio when researchers figured out one specific like key piece in the puzzle, which was that this network that models the conditional distribution that you see here, it has to have a large receptive field. And what a receptive field is that in this conditional distribution you saw, when you make a neural network approximate it, you want to be able to see as many samples as you can in the past. And that's what we typically call a receptive field, which is for any output, how many samples does it use to generate this output? So popular research papers like WaveNet and Sample RNN figure this out, and they design the architecture of the neural network such that it can have a large receptive field when modeling this conditional distribution. So moving on, I think you probably already had this in your mind. The issue with this model is, even though it works well and it has, it's pretty powerful, the issue is that it's painfully slow because you're generating one sample at a time. This is probably not a bad deal for domains like text, where your typical units are words, and you probably have a maximum of 20 or 30 words. But with audio, it's not the case, because once again, this sampling rate issue is here, where audio is at a 22 kilohertz resolution. So generating one sample at a time, so generating one sample at a time pretty much means for a 4-second audio at 22 kilohertz, you need to generate 88,000 samples, one single sample at a time. So this is a very important disadvantage of autoregressive models for the mel-to-wave network. So let's quickly summarize what is so the key issues or disadvantages with existing methods, which is number one, raw audio modeling with a low capacity model is very hard because of just the sheer temporal resolution of the data. And there is also structure at very different time scales. There's structure at short time scales, and there's also structure at longer scales, like the pitch, the intonation, a lot of things like that. And the second major issue is that high quality audio waveform generation is slow, because most existing state-of-the-art methods use autoregressive models. And like we just saw, it's painfully slow. So let's look at how we decide to solve this. It's using this method that a bunch of us at Descript designed called MelGAN, which tries to get around this issue using the Generative Adversarial Network framework instead of going down the autoregressive model framework. So the advantage of GANs is that now your network doesn't have to do it one sample at a time. It's going to generate everything in just one complete stretch. And let's see how that is possible. So this is a rough flow chart of how the MelGAN network is going to work. So you probably have heard in GANs, we have these two networks, the generator and the discriminator. And I'm just going to give a quick high-level intuition on how these two networks work. Once again, this is a very cliched explanation of GANs, which is the example of cops and counterfeiters. So the counterfeiter tries to print fake currency while the cops try to detect fake currency. And this is essentially what is going on in this network. So the generator is trying to do the role of a counterfeiter, where it's trying to generate this fake data. And there is this other discriminator network, which acts like a cop, and it's going to try to identify whether something is fake coming from the generator or whether it's coming from the true data. So what you see is these two networks sort of play an adversarial game, and they sort of improve each other or fight against each other to do their corresponding jobs better. So what happens at equilibrium is that the discriminator cannot tell the fake ones apart from the original, and the generator successfully models the distribution we're interested in, which is the raw audio waveforms. So that's a high-level intuition. And what you see in this flowchart specifically, though, is in our mel-to-wave framework, the input to the generator is going to be the MEL spectrogram. We typically use a smaller chunk of MEL spectrogram, not the entire spectrogram corresponding to the entire sentence. And what it's going to do is convert this MEL spectrogram and invert it back to the raw audio waveform. So, and then the discriminator is fed both the fake generated data and also the real data coming from the true audio distribution. And this discriminator sort of tries to build a classifier and identify which one is real and which one is fake. And so the discriminator now is gonna, the signal for the discriminator is like ground truth. You have real data, you have fake data, and the discriminator tries to get better. And the generator gets trained by taking the signal from the discriminator, and it tries to figure out how better it can fake the generation of the data. So that's it.
Rithesh, while you're on that slide, you have a question that might be related to it. The question is it a convolutional network or a LSTM RNN sequence network?
Yeah, that's a great question. So in our setup, MelGAN is a purely convolutional network. So it has a sequence of transposed convolutions. What it does is it sort of like upsamples, or it increases the resolution of the input of the spectrogram so that it can reach the same resolution of the waveform. And pretty much it's a sequence of dilated convolutional layers. So interestingly, for more details about the exact network, I strongly encourage you to look at the paper. We wrote a paper that was accepted at the NeurIPS conference called MelGAN, Generative Adversarial Networks for Conditional Waveform Synthesis. And we have written a very detailed paper, and we've also released the code so people can play around with this model. Yeah. And also, I think the slide should have a link to the paper as well. So it's going to be pretty nice. Any other questions?
Yeah, actually, while you're on here, Lee wants to know, since the choice of MEL spectrograms was a design choice, wouldn't a reconstruction to wave using a phase preserving representation be easier? In other words, just have a text to complex MEL rather than text to MEL.
Yeah. You want me to answer it, this?
Yeah, so that's a pretty good question. So the major reason why a lot of people in the research community don't do this is because generating the phase from text is pretty hard, because generating the magnitudes is very easy because there's a lot of correlation from text to the frequencies that correspond to the text. But generating the phase has typically been pretty difficult, and that's why we choose to that's why we choose to drop the phase. Yeah.
Wonderful. And one more question for you guys while we're here. The final generated raw audio is quantized, or is the final generated raw audio quantized using a mu-law distribution? And if so, which one and how big was the impact of using this type of compression?
Yeah, excellent question. So the previous autoregressive models had to do the quantization because autoregressive models for well-to-wave worked only if you quantize the audio to a discrete scale, which was typically 256 or 5000. And the autoregressive model was working only in this discrete setting. But in our GAN setting, we operate in the float, within float values. So we just chose not to do any sort of quantization.
So it's linear scale, no quantization at all.
Yeah.
Awesome. Another question while we're here. I love all these great questions. Thank you, everybody. You're making me sound very smart. Here's one I thought of. Okay, Brian wrote for me. It seems like something needs to be deciding the prosody to generate the MEL spectrogram. Is that taken care of by text-to-mel?
Perfect. Yes, that is taken care of by text-to-mel, and that's going to come pretty soon. That's
I knew that. Awesome. All right.
Yeah. Perfect.
Let's keep going.
Moving on. So, so while we spoke about GANs, just a more technical explanation of what happens. So what GANs try to do is you transform a simple distribution like a unit Gaussian, and this generative model, this generator network of the GAN, it basically tries to map this simple unit Gaussian distribution in a low dimensional space, and it sort of maps it into this high dimensional space of images or audio or whatever the distribution is. So what happens during training is initially in the GAN, the generated distribution in this high dimensional space looks very weird. It doesn't look like the true data distribution. But through training and through the signal it's getting from this discriminator, what happens is that this high dimensional distribution just gets warped. It gets warped around by this generator network, and at equilibrium, it's going to match the true data distribution after being warped around to fit the true data distribution, basically. Yeah. And what you see below is the mathematical formulation where the generator and the discriminator play a two-player minimax game with the value function that you see over here. Yeah. So moving on. So let's talk about MelGAN specifically, what we designed. So the major benefits of MelGAN is it's considerably smaller than any existing deep neural network model for audio modeling, with very high output quality. Also, another important thing is it's completely non-autoregressive in generation, like I said. So it's almost 10 times faster than the fastest available model to date with comparable output quality. And another benefit is MelGAN seems to be a very generic solution to conditional waveform synthesis applications. And I'm saying this because in our paper, we show that it not only works for inverting this MEL spectrograms back to the waveform, but it is also good at other tasks where the input is not MEL spectrograms. It can be something like encodings from some neural network, and it's still successful at inverting it back to the waveforms. Now let's look at some exact numbers when we say it's faster or it's smaller. So as you see here, MelGAN is almost 25 times faster than Clarinet, which is the fastest model to date to do MEL spectrogram inversion. So it's 25 times faster than Clarinet on CPU, and it's nearly 100 times faster than this model on the GPU, while being 2 times smaller in terms of number of parameters. So that's one of the coolest things about MelGAN, and the most interesting thing about working on this, which is that we were able to build a small, lightweight model, which does pretty well. It just does its job. So a natural question now is, do we need to do cloning for mel-to-wave? Because it seems like this task can be done without cloning, because when you do this task, you can basically invert these MEL spectrograms to the raw waveform. You don't have to use the speaker ID, and a good model trained on a multi-speaker dataset should generalize well out of domain. So this is true with MelGAN, but we definitely did notice that performance is better when we fine-tuned on limited data, as low as 10 minutes. And the reason for this is just that intuitively, you can think of it like the MelGAN model trained on this large multi-speaker dataset is learning basic patterns to invert this spectrogram back to the waveform. But when we fine tune on the specific speaker that we want, it's learning specific patterns for the speaker that we're interested in. And yeah, so in practice, what we do is we initialize this generator and discriminator from this base model that we trained on this multi-speaker data set, and then we fine tune it on the cloning data, which is typically like 10 minutes. Yeah. So I'm gonna pause here for some questions, if someone has any. Perfect. Yeah. So let's hear some samples. So I bet people want to hear some of these samples. So
Brian, were you unmuting yourself to ask a question? I saw you.
I mean, I was, but it's fine.
You're letting it go?
Yeah.
Oh, good.
All right, so let's hear some samples. So here we're going to show you how MelGAN is closing the gap towards perfect waveform reconstructions. So what I'm going to play first is some of the reconstructions for the base dataset speakers, where we had nearly 20 hours of data for each speaker. So I'm going to first play the original audio, followed by the reconstruction.
Can't remember telling my parents that I was studying classics.
Did I share the screen with computer sound, by the way? Or is it playing from my speaker?
Yeah, we can hear it.
Okay, perfect.
They might well have found out for the first time on graduation day.
And that's the reconstruction.
Can't remember telling my parents that I was studying classics. They might well have found out for the first time on graduation day.
One more.
But now my friends all seem to have forgotten. To go and socialize requires a huge effort on my part, but they don't seem to realize this at all. But now my friends all seem to have forgotten. To go and socialize requires a huge effort on my part, but they don't seem to realize this at all.
Yeah, so that we know is impressive. A lot of models can do that because we have a lot of data. But the actual impressive part is working on clone speakers where there's very less data. And let's see how that sounds.
Listen, this is very important. I forgot my video camera. Could you stop by my place and pick it up on your way to the mall? Yeah, I'm on my way. Einstein, hey. Listen, this is very important. I forgot my video camera. Could you stop by my place and pick it up on your way to the mall? Yeah, I'm on my way. Einstein, hey.
And one more.
I know what you're going to say, son, and you're right. You're right. but Biff just happens to be my supervisor. And I'm afraid
the reconstruction.
I know what you're going to say, son, and you're right. You're right. But Biff just happens to be my supervisor. And I'm afraid.
So that's the demo for MelGAN reconstructions for original and reconstructed. And as you can see, for clone speakers, it's indeed very, very, very close to the original ground truth, which I think is pretty cool. So that's it for MelGAN. So I'm going to be moving on to the next task, unless someone is going to interrupt me with some quick questions with the first task so that we can wrap it up.
Interrupting. David says MelGAN has 2 mil parameters in the second layer out of the 4 mil. Is there a reason that it's not distributed over all the layers?
With MelGAN or with the other models that I was discussing? I'm not sure I got the question correctly.
When I looked at your network, yeah, so I looked at the network here at GitHub, and you look at the parameter distribution for MelGAN. It was heavily loaded. The second layer had close to 2 million parameters, that first layer. And then the 4 million parameters are everywhere else. Is there a reason it's so heavily loaded up front in the network?
I wasn't sure about, I didn't know this exact number, but I think it's typically very loaded in the initial few layers because we want to process as much, we want to compute and do a lot of, we want to like pump capacity as much as possible in the initial few layers because we want to have as much context as possible throughout the entire mel sequence because this is where we believe like most amount of processing happens because towards the end of the network, it's typically just fine tuning. So if you think of this network, what it does is it first, like internally, it's something like it's first generating a 4 kilohertz version of the waveform, and it's sort of just building up with higher and higher and higher quality. Like it's making it 8 kilohertz and then 16 kilohertz and then reaching whatever final resolution it is. So, so we believe that the first stage of getting to the low resolution audio is the most difficult, and sort of like building more and more detail, like henceforth, is an easier task than the first step.
Another reason, Rithesh, is basically it's so even if the parameters are very is in very large numbers early in the network, the amount of hidden size that you have, like the number of time steps, is very low, and you want to do a lot of processing early because it allows you to do a lot of processing while keeping the memory footprint during training very low. So if there are just, let's say, 1,000 time steps, so even with these 2 million parameters, like the amount of hidden states that you store is very, very little. So you want to get away with a lot of processing in the early layers just for like memory constraints.
Yeah. Thank you for that, Kundan. Yeah, that's true.
Wonderful. Next. Yeah, one more question about, a bunch more questions, but one more question. This one's on multi-speaker training. It's a 2-part question. The first is, how many samples per speaker do you need? And then how many speakers are needed for the model to generalize?
Is this for the base data set speaker or for the fine tuning? I'm not sure I got that.
So I think like the question is, okay. Yeah, so I can see the question, Rithesh, so I can probably read it loud. The question is basically, how many speakers do you need in the multi-speaker case for it to generalize, and then how many do we need per speaker for it to train that model?
Yeah, so what we do is we typically have 6, we use 6 speakers for the base data. I think the amount of data is not equally distributed, but it was 20 hours each for a few of the speakers, but much lesser for the other 2. But the only important thing though was we needed these 6 speakers to be very high quality. That was the most important thing. We couldn't get away with using unclean data when training the space model. I hope that answers the question.
Yeah, were any other frequency domain representations tried, or a latent space instead of the MEL spectrogram?
I think we did a couple of experiments at some point with using latent space. We also tried some experiments. I don't know if people know about this model called the RevNet. Not too much success, to be honest. Yeah, it just worked best to stay with MEL spectrograms.
And in terms of frequency representation, we tried at least two others. One is just linear scale prediction, and then other is called CQT. And for all of these, the MEL just seems to have way easier. MEL seems to be way easier to model from text, just because the mapping is way clearer in some way and easier to learn. So yeah.
When you say reconstructed, is it reconstructed from the true MEL spectrogram?
Yeah, so the samples you hear are definitely from the true MEL spectrogram. And the reason is because we, here in this demo, we only want to show you how it sounds with this specific task of MEL to wave. But definitely we have a lot more samples coming where you see it end-to-end going from text to the entire generated waveform.
Awesome. Can you talk a bit about the level of phonetic diversity required for a successful fine-tuning? And then somebody else, Steve Chua, what's up, Steve, has a question about the minimum amount of training data needed per speaker in order for it to become acceptable. So phonetic diversity and then the minimum amount of training data.
Yeah, so regarding phonetic diversity, this reminds me of this Mission Impossible movie that I saw where they make them read a specific script, and apparently the script is really important. So for us, no, we particularly don't sort of like build an intelligent script where we need a lot of phonetic diversity. Just any recording, I think we just pulled up a random script from online and people read it and it just seems to work. So my answer is going to be, we don't particularly look for phonetic diversity. Regarding the amount of data, I can definitely say a lot of Overdub voice doubles which we've created work extremely well with 10 minutes of recorded data. So I would say 10 minutes is acceptable for a large chunk of them. Yeah.
Awesome. And then on behalf of our friends with accents, they are writing, does this generalize over accents? If you clone a non-native English speaker, is their accent maintained at inference time?
So I'm not going to answer this right now and just leave it at, there's an Easter egg at the end of this presentation that should answer this question.
Wonderful. Awesome. Thank you all for your great questions. As a rule of thumb, if you don't end your statement with a question mark, I probably won't know it's a question, but feel free to discuss and debate the benefits of U-law compression amongst yourselves. Report.
Perfect. Let's move on. So now let's move on to the more important task and the more difficult one, which is modeling text to MEL spectrograms. So once again, a quick API of this task. How this looks is the input is the text representation and the output has to be the MEL spectrograms. And the network modeling this is titled Text-to-mel because it's going from text to MELs. So the most popular choice for modeling the Text-to-mel network is to use attention-based sequence-to-sequence models. For those of you in the call who haven't heard of these terms before, let me just quickly explain each word in this title. So what sequence-to-sequence means is it refers to tasks such as text-to-speech, machine translation, dialogue generation, basically all the tasks where what you do is go from one sequence to another sequence. Like you go from a source language to a target language. You go from a context in a dialogue sequence to the next dialogue in the sequence, or whether you just go from text to speech. So that is sequence to sequence. So sequence to sequence models are typically autoregressive models, which we just discussed earlier. And the missing definition is attention. And I'm going to spend a few slides just quickly explaining the intuition behind attention. This is a pretty easy concept, people tell me, to understand, and it is true, I guess. So what attention does is when we want to do something like generating a caption for an image, so when we generate the caption one word at a time, we typically don't want to look at the entire image, because when we're captioning it, we typically look at a distinct subset of the image, like a small patch. So for example, if I'm going to caption an image as a woman throwing a frisbee in a park, when I say frisbee, I'm looking only at the frisbee, not the entire image. And that is essentially the concept of attention. So when a neural network is trying to generate a caption, we want it to only look at a subset of the image and not the entire image. And this concept of attention is very useful for us because it's not only captioning, there's a lot of tasks like generating text-to-speech, generating translations. The same concept of attention applies, it translates. So quickly going over the same concept of attention for translation and TTS as well. So what you see here in the slide is an attention matrix, which is something we popularly visualize because it sort of gives us a deeper understanding of what's going underneath these deep neural network models. So what you see on the left is an attention matrix where the row is the source language words and the columns are the target language words. And what you see along each column is the weightings that the neural network model gives to how important the source words are when it's generating the particular word in the column. So for example, if you see the column of agreement, all you see is that there's a very strong weight applied to the word accord, which in French is agreement. And this is the concept of attention, basically. So when you want to generate these words in the target language, only a subset of words in the source language are relevant when generating this word. And the neural network should only look at these words in the source language when it's decoding the target. And once again, same thing for TTS. When you are generating the MEL frames, you only want to focus your attention on the particular word or phoneme that which you're voicing, and that is what is captured with this attention framework and why it is important. So there's been a very large amount of successful attention-based sequence-to-sequence models for text-to-speech. I've listed some of them with interesting links for just further reading. But let's move on to why attention-based sequence-to-sequence models for TTS is bad. So the first thing is learning attention is often unstable, and it's difficult to scale to large multi-speaker datasets. There's been a bunch of papers recently talking about this issue and more work on how we can make it more stable. But this is still very much an open problem. The second issue, and in my opinion, this is the most important, which is these attention-based models sometimes cause pronunciation errors as a consequence of what we call attention failures. And fixing this problem during inference is very hard. And especially for a company like Descript, where we're putting this technology at the hands of people, having pronunciation errors is pretty bad. It's hard for us to fix this problem, and this is like a deal breaker for many users. So this problem especially is amplified when you use this concept called content-based attention mechanism, which is something that has to be used when scaling to architectures like transformers for efficient training. I'm not going to go into detail about these terms, and I've added links for further reading. But I think I'm fairly certain a bunch of people in this talk already know about this. But yeah, and the third reason is that attention-based sequence-to-sequence is still slow, especially with high-capacity models, because once again, they're autoregressive and the attention computation is sequential. So a very successful recent method called transformer TTS takes almost 12 seconds to generate an 8-second long sentence. So, and this is only factoring the first component into account, not even the second component of MEL-to-WAVE. And the last one is sometimes the generated spectrograms are still often blurry and not very sharp. And this causes samples to sound very fuzzy. It's not very crisp. And this is more of a problem, especially when we do cloning, because once again, we have limited data and it has its own constraints as a result. So that is an important issue with these models as well. So that is a summary of the issues. Let's actually look at one of the important issues that I said in practice. So this is one of our models, and let's hear the text-to-speech, like end-to-end sample of this model.
But considering this is actually a clone voice with 8 minutes of data, don't you think this is pretty impressive?
Yeah, so what you see on the right is the attention plot. And what you see is this model has skipped over the phonemes that correspond to the word that. So there aren't easy explanations to why this happens in practice and why it happens during inference. We also try to apply a lot of constraints to the attention to make sure it doesn't skip these phonemes. But in practice, it's still very, very hard to make this model work in a very consistent way such that it doesn't have errors like these phoneme skips. So this was one of our models at some point, which was a very good candidate model, but we never got around to solving these problem with pronunciation errors. So the solution, what we decided is to revert to the more traditional pipeline where this was before attention was invented, and people were just using this model called a duration predictor. And I think from the name, it's fairly clear what it tries to do, which is it's a model which predicts the duration of how long each phoneme has to be voiced. So now our text-to-speech pipeline looks different. So what we do is we take this text representation, which is typically phonemes. We feed it through this duration predictor, which returns a bunch of durations for each phoneme. So so it's important to remember that the input and output of this network are exactly the same in the sense that they are time aligned. The time resolution is the same. And the output is basically how long each phoneme has to be voiced in term, yeah. And what we do with this is that we sort of repeat each phoneme in the input by its duration. So what you see is just repeat of sampling. And now we feed it to this text-to-mel network to generate the MEL spectrograms. So I think in the earlier slides, we already spoke about the major difficulty of the TTS problem, which is resolving the difference in lengths between the text and MEL sequence. We looked at attention as a potential solution, but now you see that we sort of get around using attention because we use this external model that aligns the text and the MEL sequence. It also makes our job easier because now the text-to-MEL network has completely same time-aligned sequences, and it just has to convert this sequence of phonemes to the same length sequence of MEL spectrogram frames. So just summarizing the benefits of the duration predictor. So it replaces attention, it's separately learned, it provides better fine-grained control for both training and inference. I say fine-grained control because unlike attention, what we can do is if you want to speak the same text in a fast pace, or if you wanted to speak it in a slow pace, it's very easy because all you do is just multiply the durations with a constant multiplier, which will stretch or squeeze these durations to whatever we want to make it sound like. And like I said before, it helps us fix pronunciation errors because the duration predictor is pretty well behaved, unlike the attention model. Yeah. Actually, for questions? Yeah.
Well, brilliant timing. Brian, do you want to ask your question?
Yeah.
What do you mean, out loud?
Like with your voice?
Well, I was hoping you would have cloned it by now, but wouldn't this duration representation be problematic for generating different kinds of prosody? For example, a statement with a falling pitch versus a question with a rising pitch?
Yeah, that's an excellent question, actually. So this is where an interesting design decision comes in. So the duration predictor, in practice, the input is not only the text representation. We also feed it a MEL spectrogram, and then we ask it to predict the durations. And of course, the MEL spectrogram has to correspond to the exact sentence that is for which we're predicting the durations. So what happens when we feed the MEL spectrogram at the input is we pass it through this thing we call a style encoder, which kind of spits out a vector. And when we train it in this fashion, where we actually feed the MEL spectrogram, what happens is that now we're capturing interesting styles in the input MEL spectrogram. So instead of it being a very difficult problem now, where there's a lot of variance in terms of the whole different bunch of possibilities in which you can generate these durations, this MEL spectrogram basically limits it to in relation to this actual ground truth audio. So when we apply this in practice, so we want to sample, a new audio with a different text, what we now give to this duration predictor is a reference audio. So it no longer has to correspond to this exact same thing, but just a reference coming from a different sentence. And what happens as a result is it sort of transfers a lot of attributes from this reference audio into the durations of the text that you want to generate. So that's pretty interesting, because now you get this interesting thing where you can feed a reference audio which has a rising intonation or a falling intonation, or it's speaking something in a particularly fast way or slow way, or any specific speech attribute. And now we can generate them with our TTS pipeline by sort of transferring a lot of speech attributes from there. I hope that answers your question. Yeah. Any more questions? All right.
Actually, yeah, if I could. I'm quicker at saying it than typing. So you're saying that in addition to duration, which would of course make it monotonic, you do get the pitch from this reference audio.
Uh-huh.
Okay.
It's not exactly the pitch, right? So the duration pretty much only controls the pacing. It's kind of debatable if the durations also sort of impact the pitch, which probably is true in some cases. But typically the pitch is controlled by the Text-to-mel model, and it sort of learns to model all those differences.
Okay, so the Text-to-mel model is also helping guide, when you need a pitch change, as it were.
Yep, yeah, that's right.
And that's why the style thing that Rithesh mentioned, that there is an additional input other than these durations, which is just like a compressed version of this MEL spectrogram itself. So that is supposed to learn everything that is just not contained in durations of phonemes.
Yeah. So so let me just explain it this way in a high level. So what happens is when you have text and you want to generate durations for it, once again, it's a very, in deep learning terms, a very multimodal problem, right? What it means is for the same text, you could say it in a very high number of ways. So learning this duration predictor model in such, with such high variances is pretty hard. So what you typically do is you sort of reduce that variance quite a bit. And how you can do that is for the same text with which we extracted the durations, we also sort of feed the actual ground truth MEL spectrograms. So it sort of limits the durations that make sense for this text and MEL spectrogram pair. So the duration predictor is better learned. And it also gives us this control during inference where you can feed any reference you want, and it's sort of going to transfer a lot of the characteristics from that reference and apply it to the text that you want for the new text that you want. Yeah.
Awesome. And while you're here, you mentioned style. A question came in, is style an embedding?
Yep. So it is an embedding. It's basically, so the embedding comes from a style encoder. So the input to the style encoder is going to be the MEL spectrogram frames, the entire sentence, and the output is going to be one single vector. So it is like an embedding, but I would call it an encoding. Yeah. it's very low dimensional also. Yeah.
Awesome.
All right. Moving on. So let's move on to the interesting part, which is the Text-to-mel network. And we've discussed attention-based sequence-to-sequence models. We've listed a bunch of popular models. And now let's talk about what we do here. Once again, we go through GANs. So since we have so much love for GANs, let me explain how we apply it for the Text-to-mel network. So the awesome thing now is since we have this duration predictor, and since we have this time-aligned phonemes, we can get pretty crazy with how we design these networks, especially since now we have this phoneme which is aligned with the MEL spectrograms. Basically any training algorithm is up for grabs. And we use GANs in our case, and it worked pretty well. So how it works is pretty similar to what we already spoke about with the MelGAN setup. So the only thing that changes are the inputs and the outputs. So what you see as the input to the generator is the phoneme sequence being upsampled, once again, with something like a duration predictor. And the output is the MEL spectrogram. And just like the duration predictor that we spoke about, we also have a style encoder, once again, for the Text-to-mel network. And once again, for the deep learners out there, you already noticed this looks something like an autoencoder. So what happens now is the encoder learns these style vectors that are very similar to what we spoke about for the duration predictor, except that for the duration predictor, what the style encoder does is something like try to figure out the pace of delivery. But when it comes to the Text-to-mel network, it learns to things like Bob just asked about, which is pitch, or the specific cadence with which it was spoken, or the intonation, and a lot of speech attributes like that. So once again, the style encoder is very similar. It just takes this ground truth spectrogram, compresses it into a small vector, and we feed this as additional input to the generator. And the major reason why we go with this style encoder setup is we noticed that the GAN, this Text-to-mel model, just trains way better. Because once again, the Text-to-mel spectrogram mapping is very, very multimodal. There's a lot of possible outputs. And this style encoding coming from the ground truth spectrogram just limits the space of possibilities and helps us model it very well. And apart from that, a little more detail about our algorithm. It's pretty much exactly the same as MelGAN. That's also the reason why MEL2wave was discussed first, and then I'm talking about Text-to-mel, because chronologically, that's what we did. We designed this extremely good, well-working algorithm, which is MelGAN, and we sort of just applied it to Text-to-mel as well by just doing some sort of modifications that helped us get here. So that's it for GAN TTS, pretty much the same as MelGAN, just inputs and outputs are different. And pretty much the same GAN discussion that we had before. So let's talk about the advantages of GAN TTS. It's very scalable. The generator network is a multi-layer transformer, which is the most successful sequence modeling architecture. And it's also scalable because, once again, we don't have this issue of text and the MEL sequence being of different time resolution. It's the same, so we can apply a lot of scaling with a lot of ease. It does not suffer from pronunciation errors that we spoke about. We noticed that the generated spectrograms are very sharp and the resulting audio sounds crisp. And an intuition I can give behind this is that with GANs, we have this natural adversarial game, right? So what happens at some point is the spectrograms are indeed a bit blurry, but now the discriminator sort of adapts itself and it says, wow, like now you're generating spectrograms that are very blurry and this is not how real spectrograms look. And the generator uses these signals and becomes more sharp. And lastly, one of the most important things is, like we've talked about this at great detail now, we have these style vectors that we spoke about that allow us to do controllable delivery of speech. That is something a lot of people desire. So with these style vectors, we can do stuff like manipulating intonation, manipulating emotion, by picking the corresponding reference audio, which we call style audio that we want. I'm going to pause here for questions. I think I see the notifications popping up.
Yes, Brian has his mic already unmuted, so I'll just let Brian ask his wonderful question.
Okay, so if I'm understanding correctly, what I think of as providing the prosodic contour is coming from your style vector.
Mm-hmm.
And so I'm wondering, does this mean this kind of makes, depending on how you look at it, makes what you're doing ideal for Descript, or maybe forces you to generate short bits of speech that are in a larger thing of ground truth speech, so that you get the prosody sort of determined for you by the style vector being input from the overall ground truth audio?
Yeah, so I wouldn't definitely say that the Descript sort of setup forces us, but it definitely is very ideal for generating smaller, phrases rather than long sentences, where the prefix and suffix audio sort of like clearly determine the intonation of the middle part. But I think I would definitely say that in our experience, using these style vectors actually give us a very well-behaved TTS model, not just doing imputations. We get like more control over the intonation of even TTS, because sometimes what people do is they have a sort of idea of how they want the output intonation to sound. So I think you would have seen in Jay's demo where we talk about Catherine being happy or Catherine being sad. So when we provide stock voices within the app, we sort of provide the same voice and also a bunch of different emotions. And that's why I would say it helps for TTS as well. And apart from that, I think one of the other major advantages is also that using these style vectors actually helped us train a better model. The output audio sounded way more crisp, just because it was easier to train this model in an autoencoder setup than just training it like a vanilla GAN.
Sorry, one quick follow-up question. Then can you or are you taking a style vector from, let's say I'm editing, replacing frog with toad, and now I want to make the whole sentence excited. Can you like somehow average or merge two style vectors, one from the underlying Descripts, the pre-recorded speech, and one from an emotion thing that's not from the speech that I'm trying to edit, but contains the emotion I want, so I can make an excited frog sound?
Yeah, so we haven't, so we don't expose this in the app yet, but I think from what I imagine, it should be possible, although we haven't played around with this stuff too much yet. Yeah.
Okay, thanks.
Yeah.
Awesome. You had mentioned training data. A question that came from about 1 or 2 slides ago. How is the training data curated?
For what specifically? I don't understand the exact question. Sorry.
I probably should have asked it when it came up in context.
Yeah, I'm not sure where this specific training data question is coming from. Yeah.
I asked this question, it was specific to the text-to-mel and duration predictor. So the two questions, they were in sequel, is that one is, first one was, is the duration predictor and text-to-mel sort of trained together as a single training run? That kind of got answered into a subsequent slide. But the second question was, how did you go about curating specific data for this training paradigm that you had?
Oh yeah, perfect. So this answer, I actually had a slide for this, which I took down at some point. The answer is that we basically use the same approach that this paper Fast Speech does, which is, so traditionally how people train the duration predictor is we used an external forced aligner, like a model such as Gentle, which is basically a simple speech recognition model. And we just use the intermediate outputs of this model to get the alignments for the ground truth. But we instead just used the attention-based sequence-to-sequence model we just spoke about. But instead of using it to generate the MELs, we just take the attention matrix from it and then we use the attention matrix to get the durations for each phoneme. So yeah, that's the short answer. Important to note that we also tried just building a speech recognizer and using the attention from the speech recognizer, but it was just simple in the end to just use a text-to-speech model to get the attention matrix.
Cool, thank you.
Yeah. Any more?
Home stretch.
Perfect. Let's go. So let's talk about cloning now, so typically when people refer to cloning, this text-to-mel task is what people think about. So cloning works fairly well, actually pretty well, with GAN TTS. We just fine-tune all the layers of the generator and discriminator on limited data. So the most important thing is we don't have pronunciation errors anymore on the clone speakers, which was a big win, because this pronunciation problem was pretty bad majorly for clone speakers, not for speakers where you have a ton of data. And we noticed that it interestingly works extremely well even on noisy recordings. And it surprisingly works well even on speakers with different accents, which is something that someone asked about. The two caveats that I do want to talk about though is it doesn't work well on unscripted recordings. And what I mean by this is the cloning data that we require, which is of 10 minutes, we want it to be extremely consistent, where we provide a script and this person just reads the script very well, and it doesn't sound like he's making a lot of mistakes or he's stuttering too much, or it sounds very conversational. And by conversational, I mean how I sound through this entire talk. So if I just recorded myself with the Zoom app through this entire talk and I try to create a voice double of myself, it's probably not going to work very well. But instead, if I just read a script and speak it very consistently, my voice double would be pretty good. And the second thing is sometimes we notice that the speech sounds a little wobbly, for the lack of a better word. We don't notice this discussed a lot in the literature, so I don't have a better name or a typical meaning of a better way of explaining it, but we notice that this wobbliness occurs on certain words, typically on vowels actually. So that's another caveat. So that's it for cloning. Time for the exciting demo. So so what I'm going to play first is the original audio, and then I'm going to go ahead and play the voice double of the person. But it's not just the voice double. We're going to listen to a TTS sample first with 30 seconds, and then with 3 minutes of data, and then with 10 minutes of data. And you're going to be pretty surprised, but the voice double of this person actually sounds pretty fairly reasonable, even with just 30 seconds of data. So let's listen to the original first.
The main task in speech synthesis consists of mapping text to...
Oh, whoops, I went to the next slide, yeah.
The roosters had been crowing for some time, and the early pigs were already beginning their ceaseless turning of twigs and bits of wood to see whether anything to eat had been overlooked.
Yeah, so that's the original, and now you're going to hear one sentence each, one with 30 seconds, one with 3 minutes, one with 10 minutes. Ah, the slide is glitching.
The news of the baby's illness traveled quickly among the brush houses. For sickness is second only to hunger as the enemy of poor people. And some said softly, luck brings bitter friends. The news of the baby's illness traveled quickly among the brush houses. For sickness is second only to hunger as the enemy of poor people. And some said softly, luck brings bitter friends. The news of the baby's illness traveled quickly among the brush houses. For sickness is second only to hunger as the enemy of poor people. And some said softly, luck brings bitter friends.
Yep, so the last one is what you heard with 10 minutes of data. And for the closing demo, as promised, the one with accents. So this is a colleague of mine who is an AI researcher at Descript. This is how he sounds originally.
The main task in speech synthesis consists of mapping text to audio signal.
There are two primary goals in speech synthesis: intelligibility and naturalness.
And that's the voice double.
Hope you guys got a good overview of voice cloning using generative adversarial networks. It was my pleasure to do this presentation at the BISH Bash meetup. Have a good rest of the day and thank you.
Well, yeah, that's pretty much it. Thank you, everyone. That was a good presentation. Open to questions once again for now.
That was a great presentation. And if you want to stop screen sharing for 1 second, and then it'll go into like super Brady Bunch mode, and then everybody can use the reactions applause button to ridiculously bombard Rithesh with applause. It's a technical term, audio engineering term, ridiculously bombard. Amazing, amazing. So a couple questions coming in. Yeah, I have a question. What about if I want to clone in a different language?
Yes, good question. That is something that we don't have yet at Descript. We probably plan on doing it sometime in the future, but we do not have support for it right
now. Is this the same GAN TTS model architecture as in, quote, high fidelity speech synthesis with adversarial networks?
Good question. Nope, this is not that. So that paper is from researchers at DeepMind, where they tackle the problem of just going from text directly to the raw waveform, no MEL spectrograms in the middle. It's very hard to replicate. It's Google, and they have a lot of compute. But in practice for us, it was way easier to generate MEL spectrograms and not the direct waveform. And once again, the method is not exactly the same either. The architecture is different. The training algorithm is slightly different. We're more closer to MelGAN, which sort of came before GAN TTS. And yeah, so that's pretty much it.
Amazing. I really like the pacing of everybody asking your questions as you go. And thanks for your patience if I accidentally missed your question. Now is a good time to paste it in. And while I have everybody looking at the chat window, we skipped over an item on the agenda, which was the announcements part. And as Zafar would mention, when we do this in person, we open it up, you can come up, you can grab a microphone, you have a beer in your hand, and you announce like, hey, my company's hiring, or whatever. So since we have 50 people, having everybody unmute one at a time could take a while. So I'll say, open the chat window, paste your announcement in there. We'll all take a look at that for the next 30 seconds or minute or so. Feel free to copy, grab, screen share, or screen grab, whatever you want. And then if there's no more further questions, I'll try the breakout rooms. We can actually get to talk, chat, get to meet some of each other. Some of you might be lucky enough, because they're going to be randomly distributed, to hang out more with Rithesh and Kundan. Some might even be lucky enough to hang out with Bob Coover. Who knows?
Or unlucky, depending on how you look at that. Hey, but
fair point. If anybody has any problems, you can always opt out and let me know.
No. But as long as you said my name anyway, I do have a question for them before we get to the announcements. Can you speak a little bit more when you're going MEL to wave? Are the layers producing all of what you need to reproduce the phase? I mean, that's probably the obvious question. Yes, they are. But can you speak a little bit more to getting back to the correct phase and then bringing it back to your final waveform?
Yeah, that's an interesting question. So with these neural network models, it's typically not very cut and dry where wow, like this is a specific network. This only is responsible for getting the phase. And then now we're just reconstructing the magnitudes because we had a compression in magnitudes. So we get back the magnitudes and then we put them back with an ISTFT and then you get back your waveform. So you would think that we have networks which are as easily interpretable, but in practice, they're actually not. So it's a single network that just goes from the spectrograms to the waveform. And all the phase reconstruction that happens in this network is very implicit. So nothing is explicit. So it's just happening in a very data-driven way. So yeah, that's how I would explain it. Maybe Kundan has something else to share.
Yeah, I think it's exactly right what you said. Like basically, this whatever is the missing information that kind of needs to be interpolated, I would say, not generated. This interpolation is learned based on data directly, and this interpolation happens throughout the network. Like you can just see it as an interpolator network. We just see some input, and it has to get to a raw waveform directly, and it learns this mapping just via data. It includes going to full spectrogram linear scale, just magnitude and adding phases, but all of this just is happening inside the weights of the neural network.
I skipped over a whole class of questions. So thank you, musicians, for bringing this one back up. Sorry about that. Can you guys talk about the potential extensions or applications of this to either vocal resynthesis, singing voice, and applying it to music?
Yeah, interesting question. So interestingly, with MelGAN, we did try to do some sort of music synthesis where instead of using MEL spectrograms, what we did is we had this network, which is popular, called Music Transformer. And what it does is it just gives you a sort of encoding of the music, and you try to, and this encoding is supposed to have interesting information about the music pieces. And we tried inverting this this encoding back to the raw waveform, and it was pretty decent. So that's one interesting thing that we noticed. But apart from that, for let's say singing synthesis or singing voice, I imagine it should be easy to extend this technology to do music synthesis, because I would think that the sub-components are pretty much the same and can be reused. It's just that for something like singing synthesis, it would help better if you had an extra conditioning of something like a pitch curve. So I'd imagine that if you extract the pitch curve of some voice or of some song, and you try to generate it back, I think it could work pretty well. So just an additional input to the text-to-mel with something like pitch and synthesizing the mels, I think should be pretty interesting.
Wonderful. So, all right.